When we evaluate the given line integral, we have the line integral of y along the curve C, where the curve C is defined here parametrically, where we have x equals t squared and y equals t, where t is on the closed interval from 0 to 6. Also notice how we have differential s in the line integral, which means we're integrating with respect to arc length. If we graph the curve C in the xy plane, it would be this curve here. So we're integrating along this curve, not along the x or y axis, as we've done in the past. Looking at our notes below, to evaluate the line integral, we're going to write the integrand function f of x comma y as a function of t using x of t and y of t, which are the parametric equations for the curve C, and then differential s is equal to the square root of x prime of t squared plus y prime of t squared dt. We should recognize this from when we determined arc length earlier in the course. Now sometimes the curve C is given as a vectored valued function, so if it was given as r of t, we can also say that differential s is equal to the magnitude of r prime of t dt. Now before we evaluate this line integral, let's look at this graphically in 3 dimensions. So the integrand function f of x comma y equals y is this blue plane here. The curve C is this red curve in the xy plane. So we're integrating along this path, and because the integrand function is non-negative along this path, the value of the line integral is going to be the area bounded by the red curve and the blue plane. I've also graphed the corresponding red curve that would be in the blue plane, this curve here, so we can more easily see that we are determining the area, again, bounded by the plane and the red curve. Another way to think of this is, if we were to build a fence along this red curve up to the blue plane, and then determine the area of that fence, that would be the value of the line integral. So going back to our work, starting with the given line integral, we first need to write y as a function of t using x of t and y of t. We'll notice how y is equal to t, so we can substitute t for y. And again, differential s is equal to the square root of x prime of t squared plus y prime of t squared dt. So we'd have the square root, and then because x equals t squared, x prime of t is equal to 2t, and because y equals t, y prime of t is equal to 1. So we'll have the square root of 2t squared plus 1 squared dt. And now for limits integration for t, we're given that t is on the closed interval from 0 to 6, so we integrate from 0 to 6 with respect to t. And now let's simplify the integrand function. Let's write the square root using a rational exponent, so we'd have the quantity 4t squared plus 1 to the 1/2 power dt. Now we'll have to perform u substitution to evaluate this. So u is equal to 4t squared plus 1. So differential u is equal to 8t dt. We only have t dt here, so we'll divide both sides by 8. So we have 1/8 differential u equals t dt. So if needed, we could think of all of this in terms of u as, again, t dt is equal to 1/8 du, and the quantity 4t squared plus 1 to the 1/2 would be u to the 1/2, which means the antiderivative would be 1/8 times u to the 3/2 divided by 3/2, or 2/3 u to the 3/2. So in terms of t, we'd have 2/3 times the quantity 4t squared plus 1 to the 3/2. Notice here we can simplify. There's 1, 2, and 2, and 4 2s and 8. So we have 1/12. And then when t is equal to 6, we'd have the quantity 4 times 6 squared plus 1 to the 3/2, minus, when t is 0, we'd have 4 times 0 squared plus 1 to the 3/2. Simplifying, we have 1/12 times, here we're going to have 145 to the 3/2, minus, this is going to be 1 to the 3/2, which is just 1. So this would be the exact value of the line integral. As a decimal approximation, this would be approximately 145.4193. And again, because the integrand function is non-negative along this path, this does represent the area bounded by this red curve in the xy plane and this blue plane, which is the integrand function. So we just found this area here. And again, we can think of this as if we were to build a fence along this curve up to the blue plane, the area of the fence would be the value of the line integral. I hope you found this helpful.